Hello and welcome to Bay College's Intermediate Algebra Online Lectures. In this section, we're going to talk about conic sections initially, but then we're going to concentrate on parabolas. We'll see other conic sections in the next sections, such as 9.3 and 9.4. What are conic sections? Well, the first thing that we're going to look at is parabola, and we should be relatively familiar with parabolas. So what I have here is essentially a cone. Everyone recognizes the shape of a cone. A parabola is a slice of a cone, and that's why this section is called conic sections. If I take a cone and I cut it, if I can slice it through space, the shape that you would see in there would be a parabola. So this is a parabolic shape. It's a conic section, a slice of a cone. And it depends on how I slice it. If you look at if you can see it on the camera, the angle at which I cut it creates this parabola shape. Well, what if I took the cone and cut it straight across? What shape would that give me? Well, that would give me a circle. And we already know that a parabola has an equation that describes it. In 9.3, we'll see that there is actually an equation that describes the shape of a circle. The next conic section that we'll look at is the ellipse and the hyperbola. Well, the ellipse is essentially, what if we didn't cut it straight across? What if we cut it at an angle? We cut this cone like this. What you would get is an elliptical shape. If you could see this red value here, it's kind of like a circle, but it's stretched in one direction. So we could see that it's not round, it's actually oval, and that's called the ellipse. And there is an equation that describes that, which we'll see in section 9.4. Also in 9.4, we'll see what a hyperbola is. A hyperbola, you actually have to imagine two cones. One cone here and a mirror image of another cone below it. Well, if I cut this cone straight through, I get this parabola shape. But on the other cone, if I cut it all the way down through its mirror image as well, I would have another parabola, but they would be opening in opposite directions. I'd have one parabola up, and down here I'd have one parabola down. That's called a hyperbola. We get this shape here. The other cone would give us that shape over there. So these cones are essentially mirror images of each other, and that's a hyperbola. And there is an equation that describes that. What we'll see in section 9.4 is the equation of an ellipse and a hyperbola are very similar, except for one sign change. And that sign change just says, just like we saw in the previous section, sign changes mean reflections. Well, we're not just looking at a single piece. We're actually looking at a piece and its reflection cut if we had a reflecting cone. All right. The next thing we're going to look at is we're going to concentrate on parabolas, slicing that cone at an angle so that we just cut through part of it so we get that parabola shape. Now, if we recall from chapter 7, a parabola can be written in standard form. F of x equals some coefficient a times the quantity x minus h, quantity squared. And if we recall from last section, 9.1, we talked about h and k, our horizontal shift and our vertical shift. All right, so this is our standard parabola. F of x, a y value, equals a times the quantity x minus h. And where our y's and x is for this example is very important. That quantity is squared plus k, our vertical shift. If we recall how we deal with this, well, our vertex is the value h and k. So I have h, comma, k. H and k tells me the vertex. A, if a is positive, it opens up, and if it opens down, a would be negative. Our axis of symmetry, if you recall from 7.5, is always x equals the h value. This is the equation of a vertical line. So let's just say it's our library function where h and k are 0. So I have my vertex h and k, in this case 0, 0. And my axis of symmetry is x equals h. Well, I just said h was 0. So I can see everything symmetric from this h value to the right and to the left. And that's why x equals h. And this may be shifted to the left or to the right, but x equals h will always be the axis of symmetry. Now, what if we have a cone that we're going to cut, but it's not a cone standing vertically up or down? What if it's a cone laying on its side and we cut it? Well, we can describe that just by changing our axes. Here I have x equals a times the quantity y minus k. And remember, k always affects y. It's our vertical shift, our y value change. This quantity is squared plus h. So how would I graph this? Well, if we plotted points like we would in any graph, well, since these are x's and y's and h and k's, we can't really just pick points and plug them in because there's no math to do here. What we do is we use the same concept. Well, what is the vertex? The vertex is always the point h and k. So we have to apply what we looked at parabolas before. H always affects x. So h is the horizontal shift, the x value change. Well, that goes in here. It's still h. But notice the h is actually outside the parentheses. So we're treating it as if it were k. But because all points are x, y, the h value still has to go here. This is how x is changing. And then we have the k value, our vertical shift, but it's in these parentheses. And if we recall, anything in these parentheses, the sign we see here, we change it. So the k value, it's y minus k. The k value still affects y. It is a y value, so we put it in here. Our vertex is hk. So let's say, again, just like in the last example, I said, well, let's just imagine for a moment h and k are 0, 0. All right, what's the axis of symmetry? Well, because this is a parabola on its side, the axis of symmetry has to do with y. Because it's symmetric, because it's laying on its side. Maybe it opens to the right, a positive a, or to the left, a negative a. So what we have to do here is say y equals the axis of symmetry. Y deals with the k value. Y equals k is our axis of symmetry. So essentially, we have to realize because the x's and y's have changed positions, that's essentially what we had covered in Chapter 8, what we call the inverse. So these are inverses of each other. We're switching our x's and y's to get the inverse. So we switch our positions of h and k, but we never switch position in points. They're always x value, y value. We also switch this. So our axis of symmetry, instead of being x equals h, it is now y equals k. So be very careful. Look for where that x is. Look for where that y is. Which of these variables is being squared tells us what's going to happen there. And just like when we learned about a in standard form of a parabola, if a is positive, it opens up the positive values. If it's negative, it opens down the negative values. That applies here as well. If a is positive, it opens in the positive direction. Or if a is negative, it opens in the negative direction. So be very careful when we get to these inverse parabolas because they're laying on their sides. Now notice this is not written in function notation because this would not pass the vertical line test. If I have a parabola opening to the right, this would not pass the vertical line test. It is not a function. But we can still describe it. We can graph it as a conic section. All right, let's look at an example of this here. We have x equals -2 times the quantity y plus 3 squared. Now, if I notice this, the first thing I want to do is determine what is my vertex. What is my hk? Well, if we do that, what value is in these parentheses? Well, this affects y. So this is a k value. And it's always the opposite of what we see in here before we square it. So the k is a -3. Well, what's my h value? Well, because this is a parabola that's on its side, the h value is out here. Well, there is no h value. Well, that just means h is 0. So 0, -3 is my vertex. Let's go ahead and graph that. X is 0. Y is -3. So that's my vertex. 0, -3. All right? But this is a parabola on its side. So does it open to the right or to the left? Well, my a coefficient here is a negative value. That tells me that it opens to the negative direction. X is negative in this direction. So it's a parabola that's going to open this way. One other thing we could do to check is we can look at that axis of symmetry. Well, because it's a parabola on its side, the axis of symmetry is a y value. y equals k. In this case, we found k to be -3. Y equals -3. If I draw that axis of symmetry, and I'm going to label it y equals -3, a horizontal line, we can see, yep, it's symmetric above and below that line. So we can graph this just like we did with our normal parabolas. The only difference is they're inverse parabolas. They're opening to the left or to the right instead of up or down. Now, as we had seen in Chapter 7, sometimes our quadratic equations are not in standard form. Well, this is our general form. AY squared plus BY plus C. And if we recall, we could write it into a form of H's and K's if we complete the square. So let's just refresh on how to complete the square. The first thing I'm going to do is I got to have this value as a 1. That A coefficient has to be 1. So I'm going to divide all the other terms by 3, essentially. Or I'm going to factor out. Let's factor out. Just out of my y terms. So I'm just factoring that little piece out. Now, to complete the square, we take 1/2 of b and we square it. Well, half of 2, well, let's actually show that. 1/2 of the b value squared. 1/2 of 2 is just 1. 1 squared is 1. This is the value I need to add inside these parentheses. Now, if we recall completing the square, what we do to one side, we have to do to the other. So I added it over there. I also have to add a value over here. This is where we need to be real careful. It's 3 times the quantity in here. Well, if I added 1 in here, I actually changed this whole equation by 3 times what I added in there. So I changed it by 3. So I could add 3 to this side of the equal sign. But just to save us some trouble here, what I'm doing is adding 3 to this side. Well, I'm going to have to move it back over here eventually. So I'm just going to subtract it now. So if I change this side of the equation by 3 times this value I put in here, I can undo that change by subtracting that 3. That way we save a little bit of time of moving things across the equal sign. Hopefully you followed that at home. Now I can do a little bit of simplifying because I did make this a perfect square, hence the term completing the square. And I'm just going to rewrite it. X equals 3 times this perfect square, which is going to be y. And the quantity in here before I square it is what it always factors to. So that's why I like to show these steps. And then 7 minus 3 is 4. And if we look at this, this is in standard form. A times the quantity y minus k squared plus h. So now I'm ready to put this all together. I can determine what my h, or what my k and my h are, what a is. This is going to be a parabola that's positive, laying on its side, because y is the squared value. So it's going to be a parabola that opens to the right. And I know its vertex is going to be 4, -1. And I could graph that. So what is another method that we learned instead of completing the square? Well, we talked about the vertex formula. If we recall for parabolas, it was -b over 2a, and then the function evaluated at that value, -b over 2a. Plug it in and see what you get. Well, because this is an inverse, a parabola on its side, inverses, we recall, switch our x's and y's. So my vertex formula for a parabola on its side, opening either left or right, is going to be the -b over 2a is going to tell me what the k value is, because we switched them, right? It's an inverse. And then I'm going to plug this value in to find h. Now, I can't use function notation because this is not a function, right? It wouldn't pass that vertical line test. So I'm just going to evaluate the function for that value. And that'll give me the vertex formula if I just find k and then plug it in. So let's just do that. Let's do -b over 2a of this original function here. -b would be -6 over 2 times a. So 6 over 2 times 3 is 6. So negative 6 over 6 is negative 1. I just found the k value to be negative 1. If we look here, what was our k value? It's always the opposite of what we see in here. Well, that would be negative 1. So that's a true statement. It worked. We found k. Because k affects y, it is in the y value of our point for our vertex. Now h, if I plug into the original equation the k that I found, negative 1 squared is 1 times 3 is 3. Negative 1 times 6 is negative 6 plus 7. So I'm just evaluating it for that y value, the k we found. 3 minus 6 is negative 3. Negative 3 plus 7 is positive 4, my h value. 4, negative 1. And if we look back after completing the square, we got the same value. 4 for our h, negative 1 for our k. So either way you do it, you're going to come up with the same results. Okay? A lot of times the vertex formula is going to save you time, but be careful. If it's a parabola on its side, you use negative b over 2a to find k. Plug that in to find h, just as we did here. But now that we've done all this work to find x equals 3y plus 1 quantity squared plus 4. Once it's in this form, this is the easiest way to graph it. First, identify the vertex. So h and k, we already determined h is 4 and k is negative 1. So I'm going to graph this point. I'm going to go 4 to the right and down 1. There's my vertex. What is my axis of symmetry? Well, the axis of symmetry for a parabola on its side is going to be y equals k. So my axis of symmetry is y equals negative 1. And then I can go ahead and graph this using this axis of symmetry. Which way does this parabola open? Well, my a value is positive. That tells me it opens to the right. So I can now graph this parabola to the right. And I know it's a little narrower because this coefficient is greater than 1. A lot of the stuff we're working with when it comes to these deals with what we covered in 7.5. If you struggled in that section or you just need the review, go back and watch the 7.5 video, practice the problems for 7.5, and you'll be able to do it. The only difference here is now these parabolas may be laying on their side. It's x equals some y squared value instead of y equaling some x squared value. So this has been Conic Sections 9.2 dealing with parabolas. Thank you for watching.